Okay, hi again everyone. We're on page 25 of our Calculus 3 class notes in section 13.1, and I'm calling this video example 26b because we have not quite reached example 26, but I just want to get all the information we need for example 26 first. So we just got done talking about on the previous page helices. Okay, so now I want you to understand in general that the sine and cosine functions are often used to model waves or vector valued functions that show some kind of periodicity. The imagination can build many interesting space curves. Again, here are just a few. So instead of just cosine of ti plus sine of tj plus tk, if I multiply cosine of t by sine of 3t and the sine of t by sine of 3t for the I and the j components, I now get this kind of funky looking periodic climbing up, not a helix anymore because it's not in that same form, but it's similar. And then if I looks like I'm starting with the equation of a helix, but for the moving up the k axis, in the z direction, instead of putting tk, I put sine of 2tk. I can see this kind of periodic looking curve. And if I do something like this, then you get something very cool looking, but again, it's just a periodic, nice curve in space that a particle could travel along. A little bit of note here on limits and continuity, and again, I'm mostly for just completeness of our class notes, as I'm not going to hammer us hard on limits in this class, but I do want you to know that if I take the limit of a vector valued function r of t, again, remember r of t is just a vector that points from the origin out to the space curve that we are talking about with its terminal point on that space curve, and it's parameterized by the parameter t. We usually use t because t is time. So if I'm looking at t approaching some specific value of time called t naught, the cool thing is that to be able to take the limit of this vector value function, I can take individual limits, first of the x function, and then the y function, and then the z function. A vector valued function r of t is continuous at a point t equals t naught, so some specific value of time in its domain, if the limit of that vector valued function simply means that I can plug in t naught to the vector valued function. We know that makes the function continuous from Calc 1 for a function of one variable, so it works just as well with vector valued functions. Okay, derivatives and motion. So suppose we have a vector valued function, r of t is f of ti plus g of tj plus h of tk. That's the position vector of a particle moving along a curve in space, and that f, g, and h are differentiable functions of t. So these can all be taken the derivative just like we learned back in Calc 1. Then the difference between the particle's position at time t and some time, little bit of time later where delta t is small, some time t plus delta t, is the following. We call that delta r. So that's r of t plus delta t minus r of t. Looking familiar, right? The vector function then has a derivative, in other words, is differentiable at t if f, g, and h have derivatives at t. The derivative is the following vector valued function. So if I take, we use the same notation we learned back in Calc 1, so r prime of t, knowing we have a vector valued function, not just a regular function of one variable. It's a vector valued function. Other notation again is dr dt. Well, what is it really? It's the limit as delta t approaches 0 of r of t plus delta t minus r of t over delta t. And I could actually, this is not a hard proof to show that, just plugging in t plus delta t everywhere in r, and then plugging in t, subtracting, combining, collecting the like pieces that correspond with I, J, and K, and all you'll end up seeing is that, like for example, this one would be the limit as delta t approaches 0 of f of t plus delta t minus f of t over delta t, which is, we know is just df dt, the derivative of f with respect to t. So all I'm trying to point out here is that you can just take the derivative of each component of the vector. If you want r prime of t, all you have to do is take the derivative of each component of that vector.